1 minute ago, the Philippine crust shifted measurably. A magnitude 6.9 earthquake struck at 21:59 local time, depth 17 kilometers, epicenter just offshore from Bogo City. And what I want to talk to you about is not just that this earthquake happened, but what the data is telling us about how the ground underneath an entire country can move, can be measured, and what it means for the future. Because here's what troubles me most. When stress is rising right now along a 1,200-kilometer fault line that has split continents before, how close are we to another major rupture? And how do we measure something that's literally reshaping the landscape beneath millions of people? Let me walk you through what the science is showing us, because the data coming from the Philippines right now is extraordinarily revealing about how we understand plate tectonics in real time. At 21:59 local time, the seismic dashboard flashed red, magnitude 6.9, depth 17 kilometers, epicenter just offshore from Bogo City. Within minutes, two independent networks confirmed the rupture. PVOX and USGS event maps aligned perfectly, both pinpointing the same zone. The aftershock count spiked over 3,000 in the first week, each one plotted in real time. Their depth stacking along what scientists are now calling the Bogo Bay Fault. But here's where it gets interesting. The confirmation didn't stop at seismic waves. Space-based sensors delivered the next piece of evidence. Sentinel-1 and ALOS-2 satellites swept the region, capturing before and after images. Their interferograms revealed something profound. The crust had moved. Bands of color showed permanent shifts. Some zones displaced by up to 36 millimeters. Think about that. The ground moved. We can see it from space. We can measure it. But the real validation came when scientists compared the satellite data to ground-based measurements. GPS stations called GNSS captured a sharp step. 34 millimeters of horizontal shift recorded at a single monitoring site. The data from space and ground agreed within 2 millimeters. 2 millimeters. When satellite measurements and ground stations align that precisely, you're not looking at error or noise. You're looking at physical reality. The land has moved. A lead analyst at the University of the Philippines described it to me this way. We process satellite passes and ground logs side by side. When the offsets match, we know the rupture is real, not an artifact of our instruments. Their team posted the first displacement map within 18 hours. Every station labeled, every centimeter marked. A quad split montage ran together. Shake map intensity, ground shaking data, GNSS displacement readings, and satellite interferogram fringes, each system independent, all telling the same story. Stress has released along a locked fault. The crust has shifted permanently. On screen, I can show you what this means. Geologically, the Philippine Fault Zone, a 1,200-kilometer strike-slip fault slicing through the archipelago. It's responsible for many of the country's largest earthquakes. Over time, it offsets land by meters, with each event kilometers over centuries. The fault doesn't move smoothly, it locks. Pressure builds. Then suddenly, without warning, it ruptures. The land jumps. And everything we measure, every sensor we deploy, confirms what just happened. But the numbers are not abstract. They're the measured scars of a living fault system. Let me show you what this looks like on the ground. A street in Bislig City, October 10th, 9:50 in the morning. The timestamp is burned into the corner of a photo. Power lines sway in the background. A group of residents gathers outside a shuttered pharmacy. The ground beneath them is cracked. A white crosswalk that was once straight is now jagged and uneven. A Jollibee sign anchors the location so we know exactly where this is. For many here, the first sign was a low rumble. Then windows rattled. The asphalt shifted beneath their feet. Some recall the sudden darkness as power failed. Others remember the sound of concrete splitting, a sound nobody forgets. Since the main shock, local officials have counted over 3,000 aftershocks across the region. Each new tremor brings a fresh wave of anxiety, especially for families whose homes sit near visible fault traces. The scars left behind are not just numbers on a dashboard. On the outskirts of Bogo City, a fence now stands offset by several centimeters. Its posts no longer align. In San Remigio, a rice paddy is sliced by a narrow, muddy trench that didn't exist a week before, a scar in the earth. These ground-level breaks are the surface expression of deep fault slip. For those living above the rupture, the landscape itself has changed. Roads once straight now bend abruptly. Concrete steps, up or down, where the earth has shifted sideways, sometimes by just the width of a hand. But it's permanent. The earth moved and it stayed moved. This isn't the first time the Philippines has witnessed such transformation. In July 1990, the Luzon earthquake tore a 6-meter offset through the heart of Nueva Ecija. Historical photographs from that year show a national highway sheared clean, a bridge deck left hanging in space. An irrigation canal snapped and misaligned, the two ends separated by meters. Residents from that era described the ground opening like a zipper. Houses and fields torn along the line of the Philippine fault zone. The memory of that event lives on not just in pictures, but in the shape of the land itself. Long linear scars that can still be traced today. You can drive across them. You can see them in satellite imagery. The fault has written its history in stone and soil. The pattern repeats: surface rupture, visible displacement. A community forced to adapt. Every new earthquake brings its own signature, but the mechanism is the same. A locked fault gives way. The earth splits along a plane mapped by scientists and remembered by those who lived through it. The time scale is geological, but the impact is immediate. For families in Bogo and Bislig and San Remigio, the meaning of a split is not abstract. It is something they can see, something they can touch, something they can measure in the altered paths of their daily lives. Now here's what keeps scientists watching intensely. On the latest stress map, a red patch sits just south of the main rupture. Coulomb stress has increased by 0.13 bar along the northern segment of the Philippine fault zone. In simple terms, Coulomb stress is how pressure released on one fault can nudge nearby faults closer to slipping. It's like loading a gun. You push stress onto a neighboring fault and suddenly it's closer to firing. Scientists track these changes because a rise above 0.1 bar can mean a higher chance of aftershocks or even another rupture nearby. But the numbers tell a cautious story. Most aftershocks are already following Omori's law. A sharp spike after the main quake, then a steady drop in frequency. The aftershock curve plotted from the first hour bends downward. This pattern is typical after a large strike-slip event. Each day brings fewer tremors. Most are too small to be felt. The risk isn't gone, but for now, the odds favor decay rather than escalation. Still, the outlook isn't just about statistics. Local governments aren't waiting for the all-clear signal. In Bogo and San Remigio, emergency teams are out with engineers and geologists inspecting bridges, schools, and hillside roads. The head of incident response in San Remigio puts it plainly. We check every structure with cracks or offsets. If the aftershocks weaken a bridge, we close it. If a school has visible damage, classes stay suspended until we're sure it's safe. This approach comes from experience. hard-won experience. The stress map may show where the crust is loaded, but it's the ground reports that decide which roads reopen and which neighborhoods need extra watch. The science points to gradual calming, but a patch of raised stress lingers along the fault's southern extension. That's why officials keep a close eye on the data, ready to act if the numbers shift again. For now, vigilance is the rule, backed by both the model and the memory of how quickly situations can change. A sudden cluster of shallow aftershocks, especially if they migrate toward a new segment of the Philippine fault zone, can signal that stress is transferring. This is exactly what happened before the 2013 Bohol earthquake. This is exactly what scientists observed in the days leading up to the 1,990 Luzon rupture. When the stress map lights up in red along a neighboring fault, engineers and local officials know what's at stake. Scientists check the GNSS and INSAR data daily, watching for fresh offsets. Any new jump in ground position, even by a few millimeters, is logged and compared against satellite passes. If these shifts line up with a growing aftershock swarm, the risk for a triggered slip on an adjacent fault rises. This is not speculation. This is pattern recognition based on seismic history. In these moments, the focus turns to critical infrastructure, bridges, schools, and utilities sitting above or near the mapped fault line. A triggered slip here could mean new surface rupture, cracked roads, offset fences, and possibly more evacuations. The window for this scenario stretches over weeks to months. During this time, monitoring teams keep a close cadence. GNSS logs are checked at least once a day. INSAR scenes are processed as soon as satellites fly over. Field teams share updates with PIVOLCs in real time. For the rare but most serious scenario, attention shifts offshore. If a megathrust earthquake were to rupture along the Manila Trench or Philippine Trench, the consequences could be severe. Strong shaking across a wide area, the potential for a tsunami. No data right now suggests this is imminent, but the Pacific Tsunami Warning Center is the official source for any alert. Their bulletins appear within minutes of a large offshore event, and tide gauges across the region are checked for abnormal sea level changes. To stay ahead of the risk, you need to follow verified bulletins from PVOLCs and PTWC. Let me summarize what we know. At 21:59 Philippine time, a magnitude 6.9 earthquake struck at a depth of 17 kilometers, confirmed by PVOLCs, USGS, and GNSS INSAR systems working in concert. Satellite measurements show up to 34 millimeters of surface shift, echoing historic events like the 6-meter offset along the Philippine Fault Zone in 1990. Over 1,200 kilometers, this fault has shaped valleys, displaced roads, and defined the landscape through cumulative movement. Scientists have mapped a 0.13 bar stress increase near the activated segment, but the exact timing and location of future ruptures remain unknown. This is the uncertainty we always face in seismology. We can measure what happened, we can see the stress building, we can track the probability of what comes next, but we cannot tell you the precise moment when the Earth will move again. While most aftershocks decay within days, the risk of triggered slips or rare megathrust events cannot be fully ruled out. Official bulletins from PVOLCs and PTWC guide public safety as monitoring continues. What cannot be predicted is the precise moment or scale of the next major shift. For now, preparation and vigilance remain the strongest tools against a landscape where the ground keeps moving. The evidence is clear. Earthquakes reshape the Philippines gradually, not all at once. The fault moves, the land changes, the people adapt, and then we wait for the next movement, armed with better data, better models, and the accumulated memory of every earthquake that came before. This is how we live on a dynamic planet. This is how we understand a world where the ground beneath our feet is never truly still,